Let me introduce Sergio Mier from Qualcomm. His talk is on machine learning in semiconductors, a balanced approach. Sergio is currently Senior Director of Test Engineering in Qualcomm's Product and Test Group for the mobile, AI Cloud, Automotive, and IoT business units. Thank you, Sergio. Please go ahead.
Hi, everyone. Good morning, good evening. Thanks for the introduction, Zoe. And I would like just to get started. First of all, great presentation from Terence. I liked a lot of the insights in there. For the outline for this presentation, it's mainly, I want to start with the playing field on the challenges that we're seeing in our industry, in our new semiconductor advanced nodes, and also the 3D chiplets. What capabilities we have currently and we're newly adopting. And then I want to present a couple of cases. I like to think about this as components to the equation. And, at the end, I'm going to try to present the whole picture of where we're trying to push for, what tomorrow's opportunities are, and some of the conclusions as well. Okay, so the semiconductor industry challenges, regardless if it's a chiplet or a monolithic or whichever the case, we continue to see, right now it's really hot topic, the capacity. How can we get more supply out? How can we get faster times to accelerate the silicon learnings? Every new component on the equation, whether it's a new technology node or a new package type, or comes with new type of defects as well. How can we able to expose this faster than everyone else, and to be able to fix everything back into the design and close the loop in a faster way, if anything. Security, it's a great component right now. We need to keep always in check that everything that we do has to be protected. There's no good thing to have. This is a mandatory one if we want to continue to have an advantage. Last one, also package technologies. This is the reason Ara sent the invite. We are moving into this chiplet or 3D or you name it. We started with the system in package, and that was bringing interesting challenges. I do expect to see way more difficult challenges now with the lower technologies or advanced technologies and stacking these devices. What these are going to be translating into at the end of the day is going to be how fast can I get my yields into steady state or my time to market to be reached faster than before. Can I keep my cost in check as well? We don't have these unlimited budgets across the organizations and groups, and to keep the quality at the best case. To give an example on this, quality for the mobile chips started in the hundreds of defective parts per million. Right now, we're looking more like automotive for a lot of the customers' requirements. So what we're planning to do here is we're planning to push into the advanced analytics, use heavily to accelerate the validation and the learnings across the new challenges to come. In this case, the playing field that I had for this presentation, Terence actually had a good point on the first bullets. This presentation will just focus on what we're using to ensure that the learnings and all these components, call it automation or machine learning, whichever the way applicable across the board in here, whether we use unsupervised or supervised learning as well. And, probably not everyone knows about this last part, the online and offline component. So this is where the balanced approach is coming from. So what we have currently, what we're seeing, what's available, it's what I call the offline infrastructure. We have a typical case in which our suppliers, call it the foundries or OSATs, produce our test production in-house. We have multiple of them, multiple locations, multiple foundries. Data will always be flowing into our data lakes, call it, within our organization, in which different teams will use big compute capabilities, infrastructure, and visualizations to provide the insights and actions to the different functional teams. A lot of good benefits come with this infrastructure that we have been using, specifically the flexible compute power. We always get to see that during training on neural networks, or we need now GPUs, or we need extended number of cores. It's easier and very useful to get this offline compute scalable on the number of users. We have multiple people using across the globe, whether it's in Asia, in the US, or Europe. We're able to share a lot of these capabilities in there. It's secure, we can live within our infrastructure, our firewall, and also it's optimal for training and learning. There's a lot of new data flowing in, and we need to be able to understand what components are important, what doesn't. This takes a lot of time and compute power as well, which the offline is perfect for it. The visualization analysis, we're able to plug in multiple set of tools that we can use to visualize the predictions or the new features or any insights and actionables as well. I'll present a little bit more details on the next slide in here. And it's easy to deploy because it's within our infrastructure. We know when to present what model, what flavors of models in here. Just wanted to also highlight the limitations. If you want to use this for predictions on the fly, this is not your methodology, whether it's large latency. Specifically, you can talk seconds, minutes, hours, or days, depending on what you're trying to do. Any type of inference out of it is gonna be high cost for your product if you want to use it as part of the test cell as well. Latencies are also proportional to the complexity of your models. The more data, the more calculations you will see this proportionally impacting the cost. Same thing was with, if I have 3, 4, 5 models in parallel running in the same product, you will see a latency that is also directly proportional to the cost. The second one is the security on this one. And this goes directly into security, trying to use it on the fly inference at the same time. This is not gonna be, if it's not part of the test cell itself, somebody else will be handling the security here for you. And for us, this is a mandatory check that we have to be in place. And we're not gonna compromise on that for now or ever. Now, the case for the offline, why I'm saying all this is because we can actually use the analytics and the automation. The case of the monolithic 2D or 2D going into advanced or to the chiplet, it's going to be a very similar playing field here. In the case of the assisted disposition, our team has been able now to say, hey, I have a challenge. We're able to see that we have a lot of products with different foundries, with different signatures. Well, what if we start with, let's get the trigger criteria, which is whether on low yields or in high test times or abnormal bin limits, statistical bin limits. Can we be able to just provide all the analysis? Is this a setup problem? Is this a process problem? Is this a design problem? We're a fabless company. We depend completely on the data that is provided to us, not everything, just what is provided. We control from the test onwards, from the probe. But it's our job to make sure that we have all these inputs and we're able to get the automation to say, this is a test cell problem. This is a process most likely because of XYZ, or this is a design based on this type of signatures. We have multiple types of wafer pattern recognitions. You can see some of them in here. It can be a step pattern. It can be a specific radical type of problem, or it can be a process with a localized signature. At the end of the day, what we're looking for is actionables. Can I get to start on step number 4 instead of step 0 every time I get a question or a problem on this one? The case in place here, we always have to maintain a new training on the model. Even though we get great value out of it, we reduce by 10x the time to get this type of actions compared with the previous, the legacy method. We have now also consistency across, mature nodes. This is perfectly, like a well-oiled machine in here. And it enables the teams as well to identify very accurately abnormalities in our parameters. But the problem is, again, somebody will have to always keep it up in case you're going into an advanced models or some advanced technologies. Your INCOV will have to be changing over time. Your spatial wafer pattern recognitions will be changing over time. And if your model is not trained to improve into it, then your prediction accuracy will be going down over time. So these are some of the points. So what's getting adopted for now is the online infrastructure. This is something relatively new to the industry. And we've been able to work with some of the tester vendors, and they actually have been able to provide this product out. And so why this is important is because we're looking to have a zero trust environment, which means we control completely the security of the model. We see every model as part of our IP. We're not gonna just put it out there for anyone to just be able to download or to be having access to it. So in this case, what benefits we're seeing with these inference servers that are now getting part of the tester is you have the security, you have on the fly decision making in there. And by this decision making, I'm saying you can go beyond the API capabilities of your tester. Case in place is going to be the next example that I'm going to give, but we can expand to use some of the open source analytics or the machine learning algorithms available there without having to implement all the code as part of the solution. We have minimum latencies on this one. On inference, we can go into the microseconds or milliseconds, which is okay, acceptable across the cost. And it's easy to integrate as well. What the limitation in this case is just for inference purposes. You're not gonna be able to have a great compute power to learn new features on the fly. And this is also limited on availability at the fabs or the OSATs. So these are the two areas of the limitations. However, having this capability took us to this next case, the online capability. So in this case, how we start using this tool or this hardware was we wanted to understand a specific parameter. Now this parameter, there was nothing available for us to say, hey, this is how you calculate. What we end up doing is we use some of the neural networks available, and we were able to replicate very closely the parameter that we were looking for. And it had a lot of dependencies on temperature and power and this type of sensors available. Now, the beauty about this analytics is now we can put it as part of our tester, and the tester then provides the inputs into the inference. The inference will provide the result, and we can see now our test times get reduced significantly. We don't have to iterate multiple times. We get, a huge benefit. Not sure if you can see that in here. I see a lot of the panelists. Let me. There. We can see that most of the test time, almost 50% on those type of tests, we were able to reduce it with zero impact on quality. We were able to match very closely. We were able to extend beyond the capabilities of the APIs available in testers. We were able to also run multiple models in the same project with the same inference hardware. We're able to identify performance matching components on every device. Going into the chiplet, one of the questions was, how do we select capabilities? In the previous presentation was 99% over time provides you 26% overall yield. Well, this is one of the components that we plan to start also using and identify how is this component going to match with this other type of components, and at least have an option available to the team to use. Last thing is also negligible test times. At this point, it's becoming almost zero cost for us. Again, the limitation on this was the scalability on this inference hardware to be available at the SATs or at the foundries. whatever the test houses are going to be. And there's limited adaptation over time, which means at some point somebody has to retrain this. And this goes beyond the scope of we can get the typical features to understand why and provide some causality into the problem. Now, I said the components of the equation. Now I want to address what we're trying to really address with this that will be also applicable to the main topic. We have a constant challenge, which is the adaptability over time of any type of model or analytics that we're going to be providing or generating. What I'm showing here on the chart is what we know is that the process, which is, I'm talking about defect density or process, is in the blue line. Overall, you see that the defect density continues to improve over time, regardless of what technology node you are. However, the test support usually is available until you send it to production and it goes into steady state. At that point, there's minimum or limited support. However, you come with a new variable, call it a chiplet 2.5 or 3D, and you will see that this steady state, now the tail most likely is going to start pushing out because there's always new. And the question is, well, is there anything that we can include in our models to contain the variability aspects of this type of process? Specifically, I'm looking on the right side, we have multiple areas, sites that we're using, whether it's a foundry or a probing capability. There's gonna be multiple sites, multiple foundries. Probing, you're gonna have multiple probe card vendors at that point. And everyone has different type of performance. You have different assembly houses as well, or sites in this case, or packages. You have the package test, you will see that even within the assembly house, they also change or adjust their process to continue to improve. Remember, we are only able to see a black box from our side. So we need to understand very well when anything changes, why it changed, and what its impact is as well. We have multiple SATs, test cells. You can have a tester with a different brand of handler or prober, and you will have different performance as well. If you don't understand these capabilities or limitations, you're bound to be living on that long end tail, trying to understand that as well. Power and thermal, I joke around with my team here. Most of my gray hair is coming from this type of challenge. Mainly, we have process, lower technology nodes have brought up higher amounts of power and thermal as well. This limits, in a lot of ways, your capability to move fast, and also brings new challenges to the DFT or to the package, or, I expect on the chiplets, there's gonna be a lot of interaction on this side as well. And we need to understand what its impact to performance, whether it's because of the micro bond power or because of the temperature that is going through the dies. Defectivity, it's also, again, when I see that there's higher thermal dissipation required, there's a different type of defectivity that I'm noticing as well. And setup, we have a handler that is capable of cool down, or a prober that is capable of cool down, but there are some limitations there as well. And we need to make sure that we have this in our equation. The process, defect densities, binning, I can go over every single one, but the point is, even on the defect detection, we have different type of defects that we're finding on lower technology nodes. And now I expect to see the same with chiplets, whether it's in the memory side or in the functional or in the structural. The previous presenter was actually very clear there, and I agree. We need to have the capability to isolate, and we need to have the capability to test together on this one. But all these components, they have to be part of your data. You cannot expect the machine learning to be that smart that you can ignore all these type of inputs and expect to identify specifically those type of interactions. These capabilities have to be part of your data. If you don't plan your solutions with this in mind, expect to be on that long tail for way, way long. This is, at the end of the day, what we're looking is the opportunity to bring these learnings after the steady state. Can we accelerate it and being able to kill as much of these defects as possible. So how can we enable this adaptability in our side, in our machine learning models? What we know right now is the type of variances come from a specific type of data available. We're gonna be going into a higher dimensionality in our data sets, moving from the fabrication or basic functionality on our tester or spatial and time that we all know about. Well, how about if we start now adding these capabilities of aggregating our reactive attributes? We have a failure analysis, diagnostics, we have customer returns, quality excursions, abnormalities, you name it. These have to be part of your data as well. All of this is going to be enriching your complete data set that you can run your algorithms and be able to at least expose the signatures that will give you the insights. The data at the test, at multiple operations, as mentioned, we're gonna be going into single wafers, into a stacked wafer, probably into whatever is gonna be the chiplet. Well, we need to have a common test attributes, and we see how is this performance, how is the temperature, how is the power, how is defectivity going across the board. And we're able to at some point separate when this signature is for good devices versus the bad devices. And this has to also make it into our data. Structural attributes. This is something that, I'm noticing a lot, not only, in the semiconductor industry, across a lot of functional teams, is the lack of pre-silicon and post-silicon to work together. A lot of these attributes, lack of the setup and hold, fault types, fault coverage, and the domain classification. We need to work closely between the vendors of the ATEs along with the EDA pre-silicon vendors and provide these capabilities to be coming together. Same thing goes with the topology and the layout. You name it. There's multiple areas and dimensions that we can start including to provide these strong failing signatures. We have been able to see a lot of this already in some of our limited experiments. And so where we're going with this, today's strategy will be tomorrow's opportunity. How? Well, what we have today is we're using supervised learning. We create models, that's how we start. Then we go into unsupervised learning to explore data. We rely heavily on offline infrastructure to create our patterns, our models. We apply them into the high volume manufacturability. And then we have to evaluate, and upon degradation, we just revise the model. And then, we continue the cycle. We just increase to see more models over time. What we're seeing now that we're gonna be pushing for is, first of all, higher dimensionality is a must-have at this point, if you really want to close the cycle loop time. Second part is we're gonna have to move into hybrid models, which means this unsupervised is a very powerful component of the equation. Every time you have patterns shifting over time or data shifting over time, you need to be always having this capability to question what's changing and then being able to adapt accordingly your models. So we can always be adapting it on the fly if possible. If not, have a capability to adapt with automation and having the online and offline capabilities as well. This is where I believe this is the next step for where the industry is gonna go on this one. So what is in the not so distant future? Not only we're gonna start with our baseline set of features, but also we're gonna have to create our own exploratory features. A lot of them we may have a good idea for now, and others is gonna be an iterative process that we're gonna have to make use to enrich this. Call it from the fault types or EDA or hardware from the vendors or software or system or whatever. This is going to be part of our bring up now. We cannot just be looking at the baseline anymore. We have to enable the adaptability with the hybrid learning. It's not only I am able to identify the problem, but also you would like to see your shifting. Is your model able to catch those shifts? And are you able to adapt? A specific case in place here, the wafer pattern recognitions. We start with the typical, 6, 7 fundamental type of shapes. Well, what if I tell you that suddenly you get a 3, 4 different type of signatures that had nothing to do with your other initial baseline models? your models will predict always. So your model should be able to say, I don't know. I love this concept. A professor from Santa Barbara provided this learning, and let's see why, by the way. And he says, our models has to have the similarities to what the person will say. If you're giving a data, you don't know if this is something that you should be using your knowledge into or not. You should be able to say, I don't know. And when you have a lot of these I don't knows, you can create your own supervised and say, well, from all this data of I don't know, can I create something that I know? And this is the adaptability that will come in very handy. Lastly, application. We're gonna be relying not only on the offline type of training, learning, application, but also I believe there's gonna be a heavy move towards the online test as well. And this is going to be, making use of additional capabilities from the test cells. So this is where the balanced approach is coming from different areas. Now, in conclusion, what we see in today's methodologies is we're going to continue to increase the adoption of automation and machine learning. Regardless, we want to accelerate the learnings. We want to understand better why the package, why the thermal, why the power, why the defects. We're going to reuse a lot of the sensors. I mean, there's new DFT, and what I'm noticing is a lot of the new capabilities for these chiplets are in the make. A lot of the companies are trying it. So this is going to take a little bit of time in this one to get to a maturity level that is completely adopted. In the meantime, we're using what we have, and we want to understand what the impact to the package, the process, or anything will be based on these signatures. We're using our traditional system on chip machine learning techniques, and we're gonna try to extend it to the 2.5, 3D, or chiplets, whichever the case is gonna be. We're gonna continue to use the supervised, learning or the supervised as well, and trying to at least get our short-term business challenges. Moving forward, and this is the call for arms, is gonna be, we need to really start developing application-specific sensor and hardware that will help debug and analyze the findings. It was interesting to see that P2929, and but we're gonna have to also try to get EDAs and ATE vendors to start working together to provide this connectivity between the pre-silicon and post-silicon environments, and really start getting to have this synergy to help. We're going to have in the next one also 2.5 to 3D new features. I expect different defectivity over time, and the data vendors will help a lot. There's a lot of capabilities we can use in this case. They have a lot of the capability to transport data, and we're able to use our knowledge to understand and create these new variances. On the machine learning hardware test cells, we need to start creating this dumbed down test that as we know it, and make it smart. We have the capability to use an inference. We have the capability to use our workstation, our prober, handler, everything. And we should be able to adapt over time, and having this unsupervised learning as well on the fly without impacting the throughput. It's a multi-dimensional challenge in here. And finally, the hybrid models. This is where I see that we're gonna be receiving, and probably we are already in this era, that we have terabytes of data per day. Going into the next is going to be a challenge if we continue to use our existing methodologies. Having said that, I think I am done. Thank you for your time.
Thank you, Sergio. That was a very interesting presentation. We have one question here in the Q&A. If you have more questions for Sergio, please put them in the Q&A right now. From Benny Wang, how do you validate the machine learning model and reduce the bias to avoid some test escapes?
Sorry, can you repeat the question?
Yeah, so the question was, how do you validate the machine learning model and reduce the bias to avoid some test escapes?
Yeah, so this is an interesting, we have to use some sort of sampling capabilities always. You cannot just start predicting without having a capability to give you the feedback on this one. So having always a sampling methodology that will allow you to say, you should have predicted this. However, I'm going to test everything, and let's make sure that what you're doing is able to. This gives you at least the initial feedback to say your model continues to be relevant and the accuracy as expected. Not having this, you're opening yourself to have a quality problem over time.
Thank you. Another question just came in from Phil Nye. For heterogeneous products, where are you purchasing chiplets from other companies, and how much data do you get from the supplier for these chips?
Yeah, that's actually a good question. And how's it going, Phil? It's a problem because we don't get a lot of the data. And so what we're doing is we have to generate and characterize a lot this type of devices as well. Can it be anything, in, whether it's a memory or whatever is the other heterogeneous? On our case, even we treat our own devices as completely unique. Even though we have the data, we have multiple teams that work into it. I'm part of the digital. If I get to see an analog with a digital device, I mean, I can always ask, but I would like to just collect all this information of features that I just showed in the presentation. I don't think everyone has them. And for me, it's imperative to have it available. So we would like, as we're going into this direction, to start preparing the way and communicating if we can actually get this type of features as part of the spec or of the characterization.
Yeah, understand. Yeah. And a question from Anonymous. What are the data sharing challenges, if any, and how can they be overcome?
The data sharing. Give me a little more context on that. So I can take it 10 different ways.
I'm not sure the person would have to type the context on the background of where the question is coming from.
I'll take it from the part that, you know, we are a fabless company and there's not that much of the data sharing there. Nobody wants to open their scenes out. All right. There's a lot of, I guess, details that not all the companies would like to expose to other partners as well. And that's okay. I mean, that's expected. One of the problems that I have is a lot of the failures or challenges that I'm having, defects, they happen to be related to an area that, you know, the data that the vendors or anyone provided, they're not really open to share. So it's a back and forth iteration. What I'm trying to see is instead of having 10 iterations, we get 4 the first time and then 2 the next time. And how can we get these changes or I call it variations, right? The components, if we can understand them better with our extended characterization.
Right, understood.
So that's the challenge.
Yeah, there's one last question from Supar Shinder. Would it be better to have digital twins for testing for such complex structures and their behaviors before one develops the test data analytics? Perhaps.
I'm open for suggestions. I actually, you know, this area is very new. I wish I could, you know, I'm glad to see these forums where I can learn from other people. It's not like this information is out. We're trying multiple very creative ways to address proactively. I mean, everyone can react, but the challenge is we don't have the time to react a lot of times. Your competition will eat the cake by then.
Right.
So.
Okay. Yeah, thank you.
I don't have a clear answer to that one.
We're all learning this together.
Yeah.
I think that was the end of the questions. So thank you very much for a great talk.
I'd like to thank all the presenters who presented today, and I also want to give an extra special thank you to all the sponsors who made this event possible. Our diamond sponsor is Amcor, with differentiators in technology, quality, and service. Our emerald sponsors are Advantest, rated #1 in the VLSI research for ATE survey. Synopsys from Silicon to Software. And our Ruby sponsor, Tech Search International. So I'd like to thank all of them once again for making this event possible. I'd like to thank all of you for attending and look forward to seeing everybody here back again tomorrow. So thank you and have a good rest of your day.